you're going to be doing a quadratic. Unless the numbers happen to work out nicely so that you can factor it, which apparently this could have been, but.
And you're fine with this just, graphing it, right, and then just finding where the x-intercepts are?
Yeah, the quadratic, graphing the quadratic.
Yep. Right. Technique one.
Oh, there's more.
Oh yeah, there's 3 techniques.
Oh,
The third one is the one I like, but some people like this one. Just whichever method you pick one and learn it. If you start learning all 3 of them, which would be great if you can learn all 3 of them, but too many students try to do that and then they start mixing and matching and it doesn't work out well.
And you can, like, there's not just one that works, like, cause my mind goes to like math where you have like all these different scenarios and they only work under certain conditions, but like.
And this works for, so the solution here is they're all for the perfectly elastic collision.
Yeah.
So kinetic energy is conserved and one-dimensional.
It's just that some of them are easier for some people than others.
Yeah.
Okay.
You know, the right technique is the one, the way your mind is working at the moment you need to use it.
Yeah.
All right, so let's get rid of some of this stuff. Let's just do it in general code. I have M1, and I'm just going to use A for the initial velocity of the mass 1 initial. This is velocity of 1 initial. Plus M2B equals M1C plus M2D. That's why I use C and D before, because I wanted A and B to be beforehand. This is conservation of momentum, mass times velocity, initial, mass times velocity initial for the second mass, and then finals. Kinetic energy is conserved in the perfectly elastic collision, so I got 1/2 M1A squared plus 1/2 M2 B squared equals 1/2 M1C squared plus 1/2 M2 D squared. Two equations. In a typical problem, we assume that we know what A and B are, and we're going to solve for C and D. So the second equation, first thing I'm going to do is I'm going to just multiply by 2 to get rid of the 2's. Or divide by 1/2, whichever way you like it. Now for both equations, I'm going to get all of the M1's on one side and the M2's on the other. So for the first equation, this becomes M1A minus M1C is equal to M2D minus M2B. For the second equation, I get M1A squared minus M1C squared is equal to M2D squared minus M2B squared. Now let's factor. Let's factor this one first. And how do you factor A squared minus C squared?
Oh, so
Yeah, the square root of.
the difference of 2 squares.
That is the difference of 2 squared.
Yeah.
We're going the other way. What 2 binomials do we multiply to get this?
A minus C, A plus C?
Right.
Oh, yeah.
Never mind. I was going to give you the sign of an angle, illness.
Yeah. Oh, yeah. No. All right. So I factored my kinetic energy equation into 3 factors here. I'm now going to factor that all goes together. I'm now going to factor this one, and it's just I factor M1 out, A minus C, and I factor M2 out, D minus B. So I have two equations here. This is from kinetic energy conservation. This is from momentum conservation. Linear momentum conservation, if you want to be slightly more pedantic. Now what we're going to do, divide. What's on the left-hand side is equal to what's on the right-hand side, so I'm just going to divide my left-hand side from the kinetic over the left-hand side from the momentum, and then divide the right-hand sides. Because again, the math people tell me as long as I divide both sides by the same thing, I'm good. And so I'm dividing, they're equal to each other, so I'm dividing both sides by those. A1 cancels, A minus C cancels, and I'm left with A plus C. But on the right-hand side, M2 cancels, D minus B cancels, and I'm left with D plus B. I'm now going to get the initials together and the finals together. In other words, bring B over to the left, C over to the right. So I have A minus B is equal to D minus C. This is generally the way, well, let's stick in the original letters. This is V1 final, sorry, V1 initial minus V2 initial is equal to V2 final minus V1 final.
So where did you get, okay, so I can see where you got the first equation from, or the second equation, and where you have like, yeah, I can see where you got the one below that from, but where'd you get the first one from?
Where do you get this one?
Yeah.
From this equation here, I brought M1C over to the left-hand side and M2B over to the right-hand side.
Oh, okay. Okay.
Don't you still have two variables?
We do.
Oh, so you're not done?
No.
Okay, sorry.
Let's at least put it, well, let's solve it and then let's put it into context of what we just did. The answers are erased, so this will go off memory or you'll tell me. Oh, don't use markers on this. So in our problem, I had the 5 kilogram mass going at 3 meters per second to the right, and then the 2 kilogram mass going 4 meters per second to the left. My total momentum beforehand was 7, and that's going to be equal to 5c plus 2d. That same conservation momentum equation we had, we just did it. We now have this equation down here. I'm ignoring, well, it's built kinetic. Right in. Conservation of kinetic energy is built into this. So we have 3 minus -4 equals D minus C. I have two equations, two unknowns. And if I just solve for D here, D is equal to 7 plus C. Plug that in. So 7 is equal to 5C plus 2 times 7 plus C. So 7 is equal to 5C plus 14 plus 2C. -7 is equal to 7C. C equals -1 meter per second, which is what we had before. And D is just 7 more than that. And those are the answers we had before.
I like that one.
You like that one more?
There's not a quadratic in it.
Yeah, quadratic's already been taken care of. The quadratic is built into this. The big advantage of this one is no quadratic. The disadvantage, you don't have that immediate feedback of whether you made a mistake or not. But the question I'm asking you is, what happened to the they didn't collide solution? At what point did that disappear?
Oh.
Will,
When you divide it out.
why did that take out of that solution?
Divided it out.
Because the squares are gone.
Yeah, not the squares. So this step right here, this is the step right here where it disappeared. You're right on that one. Why did that eliminate they haven't collided solution?
Wait, you're taking out mass from that problem, right?
Yeah, nothing wrong. I mean, that mass on top and bottom, so they canceled.
Oh, the negative value is gone, but not the positive now, so there's, I mean, there are two values for each side, and you took out one of them,
Yeah, but why does that eliminate the no collision solution?
because there's a plus or minus in the
No.
quadratic.
It's like Will's about to come up with something.
Does D minus B equal the initial velocity? Or is it?
A and B are the initial velocities, C and D are the final velocities.
I don't know how to explain it other than that you're just taking out a factor.
Just cancel out. So the initial and final are the same because they haven't moved, right?
Well, they haven't collided yet.
Or yeah, they haven't collided, so they just cancel out.
Careful about that. What do you mean they just canceled out?
Oh, I mean like, well, they're the same value but opposite, so they just, I don't know how to explain it.
You looked like you were almost there and then you went wandering. All right. A is the initial velocity of the 5 kilo, in our problem here. A, initial velocity of the 5 kilogram mass.
Yeah.
C is the final velocity of the 5 kilogram mass.
Yeah.
If they don't collide, what's the relationship between those two numbers? And therefore, what is this equal to?
0.
And what do the math people tell us?
Can't divide by 0.
As soon as we did that division there, we built in the assumption that they are not equal. And that's where it goes, because at the moment we divide, so you're right on that, Will. At the moment we divide, this is only true if this is not 0. So no quadratic, but we don't have the immediate feedback because we eliminated one of the solutions. Questions to hear? All right. Third technique, the one that I prefer. Oh, sorry, before we get there. This right here, this 3 minus 4, sorry, 3 minus negative 4, this is the V1I minus V2I. If I were in the 5 kilogram mass, I'm sitting right there, from my point of view, I'm not going anywhere. How fast is the 2 kilogram mass coming at me then? From my point of view, it's the 5 kilogram mass. Or we can flip it around from the 2 kilogram mass's point of view, how fast is the 5 kilogram mass coming at it?
1 meter per second.
7 meters per second?
Yes. From the 2 kilogram mass's point of view, if it's at rest, the other mass is coming at it at 7 meters per second.
Yeah.
Known as the relative speed of approach. After the collision, that 7 is how fast, from 5's point of view, how fast 2 is moving. So however fast 5 is coming at 2 before the collision, is equal to how fast 2 is going away from 5 after the collision. The relative speed of approach equals the relative speed of recession. That's the terminology usually associated with it. Relative speed of approach, relative speed of recession. Yes. And by the way, if you're doing the second technique, you don't have to do all this. You can if you want to. Just like the student I tutored years ago, who whenever needed to solve a quadratic equation, completed the squares. In essence, derived the quadratic formula every single time.
Yeah, it's,
It worked for me. You can do it, it's just a lot more work in my opinion. All right, so I've got a 5 kilogram mass and a 2 kilogram mass. All right. So if I'm in the lab frame, the lab frame is, I'm standing here in the lab and I'm watching this happen. It's basically, it's the frame of reference as the problem is giving. It's generally considered the lab frame. The velocity was 3 meters per second and negative 4 meters per second. P5 and P2. And so this was 15 and negative 8, and we get a total of 7. Stuff we've done already. And suppose instead, so I got this mass moving on 3 meters per second that way. Suppose I'm observing it and I'm also traveling 3 meters per second in the same direction. How fast will this appear to be going?
Same speed as you are. It's like the same like velocity you are. Or is it
Well, from my point of view though, how fast is it going?
It's not moving.
Right, it's not moving, from my point of view. We're matching each other. It stays in the same position.
but it'd still be moving.
Pardon?
It'd still be moving.
Relative to what? Movement is always relative to something.
Yes, you like if you're moving and it's moving, it seems like you can still tell that it's moving. That just confuses me.
Generally, when I say it's moving to the right, in the lab frame, from the lab, assume the lab is sitting still, it's moving 3 meters per second this way.
Okay.
I change the observer. The observation is no longer from the lab frame, it's no longer with the lab at rest. The observation is now with, I'm observing it and I'm moving along with it, so it's always in the same position.
Okay.
So, the velocity of the observer, 3 meters per second, and so if this one looks like it's at rest. How fast does this go relative to the observer?
$7 meters per second.
Close.
Negative.
Yeah. In essence, however fast, whatever my velocity this is, subtract it 3 on both sides. Suppose the observer is now going negative 4 meters per second. How fast is the 2 kilogram mass go?
0.
And how fast does the 5 kilogram mass go?
negative 4. No, 7.
7.
7.
We added 4 there, we're adding 4 here, 7.
Oh, yeah.
All right. Let's take a look at the momentum in the second one here. What is the momentum of the 5 kilogram mass?
Sorry.
Pardon?
I just want to what you asked.
What is the momentum of the 5 kilogram mass in this middle scenario?
0.
0.
Yeah. What about the 2 kilogram mass?
Negative 35.
30 positive 35.
I'm getting negative 14.
Negative 14.
Negative 40.
Oh, mass is 2.
Oh.
So my My total?
Negative 14.
In this other frame down here, what is the momentum of the 5 kilogram mass?
35. And then 0, and then 35.
All right, so the total momentum changes depending on the observer,
Yeah.
but momentum is still conserved regardless of the reference frame. No matter how the observer is moving, the total momentum is going to be conserved.
That's great.
Obviously, not conserved from here to here, but in one reference frame before and after collision, momentum stays the same. So what I want to do in the third technique is find the momentum frame where the total momentum is 0. I want total to be 0. I'm going to do it the long way, and then we will notice, hopefully, we will notice where we've seen the answer before. So all I did to figure out how fast the observer needs to go is I subtracted the velocity of the observer from the initial velocity. So I have 5 times 3 minus v, so this will be the velocity of the observer, plus 2 times negative 4 minus v is equal to 0. I want to have 0 momentum, and I need to figure out what that reference frame is. Solve for v, 15 minus 5v minus 8 plus negative 2v is equal to 0. 7 minus 7v equals 0. 7 is equal to 7v. V is equal to 1. This is the velocity of the observer. That's a positive 1 meters per second. Let's see if this works. What is the velocity of the 5 kilogram mass in this new reference frame?
2 meters per
2
second.
meters per second. And then negative 3.
Negative 5
Negative
meters per
5.
second.
Momentum of the 5 kilogram?
10 units.
I take ours. And for the 2 kilogram mass?
Negative 10.
Negative 10.
All right, so we nailed it.